Look at any modern technology, from a semiconductor production line to real-time medical monitoring, and you will find massive systems producing high-dimensional data. When a single variable shifts in these systems, thousands of others can react simultaneously. This complexity makes it difficult for a human operator to track the cascade and identify the specific source of a problem. Theoretical physicists have faced this exact mathematical wall for decades. They've been trying to map the chaotic, high-dimensional tangle of the quantum realm onto the smooth, predictable laws of gravity. While trying to reconcile these two halves of the universe, physicists built specialized math to compress and structure quantum chaos. As it turns out, that same math can be repurposed to organize the massive datasets we struggle with today. This mathematical framework is called Tensor-Network Quantum Gravity, or TNQG. We don't need to treat it as a comprehensive theory of the universe. Instead, we can look at it strictly as an operational software engine. Even without proving a single thing about physical spacetime, the underlying algorithms built to test this framework are fully functional right now. By borrowing the equations designed to simulate quantum gravity, we can feed in our own data problems and let the engine sort out the chaos. Here is a diagram showing how the algorithm processes a tangled web of raw data. It scans the entire network to identify information bottlenecks. It measures the flow of data across every connection and highlights the specific clusters where that flow gets restricted. Next, the engine assigns physical distances based on how strongly connected the data points are. If two variables share a lot of information, the algorithm pulls them together. If they barely interact, it stretches them far apart. Then comes the translation step. The algorithm takes this reorganized map and forces the complex network to drop into a smooth, readable 3D surface. In mathematical terms, this is a latent geometry. Because this engine is built on the equations of gravity, it comes with a built-in error check called a residual. If there is an anomaly hidden in the original data, it manifests physically as a warp or bump on this new 3D surface. The geometry engine uses the math of gravity to translate unreadable numbers into a visual shape where errors can be identified through their physical geometry. Consider industrial manufacturing. Modern semiconductor microchips are so dense and complex that engineers can no longer simply look inside to visually inspect them for internal defects. This diagram shows what happens when we feed a chip's electrical sensor data into the geometry engine. The electrical flow translates into a physical surface, and a hidden manufacturing defect develops a deep geometric crater in the corner. In the medical field, researchers face a different roadblock. They need to train AI on vast amounts of patient data, but doing so often creates a risk of exposing individual records. Tensor networks solve this by acting as a mathematical filter. Hospitals can process their records through the network, sharing only the overarching geometric shape of the medical trends with the AI, mathematically shielding the individual patient details. For defense and national security, the focus is resilience. Advanced navigation systems are vulnerable when standard GPS signals are jammed or denied. Instead of relying on external satellites, engineers use TNQG algorithms to map arrays of internal quantum clocks and inertial sensors. The math identifies structural bottlenecks caused by environmental noise, isolating the errors before the navigation system actually fails. Whether inspecting microchips, securing medical records, or stabilizing military navigation, the core approach is the same, finding the underlying geometry within the noise. There are strict boundaries to what this technology can actually do. It does not manipulate physical gravity, provides no clinical medical treatments, and offers no weaponization capabilities. As an actual theory of physical spacetime, tensor-network quantum gravity remains entirely unproven and conjectural. That separation leads to the primary rule driving this research. Do not try to sell the unproven conjecture. Sell the validated, primitive algorithms. The immediate next step is pulling these mathematical tools out of theoretical physics departments. By putting them into rigorous, phase-gated software labs, we can build functional diagnostic tools today. Science doesn't always need to reach its theoretical destination to be useful. By attempting to solve the mystery of spacetime, researchers developed a way to see the underlying structure of our most complex industries.